Hi everyone, this is Abhilash, and today I will be taking a session on accelerating Pytorch with IPEX. IPEX stands for Intel extension for um, Pytorch. So a little bit about me before we start the session. Um, I am a supercomputing engineer working at Intel, uh, working on distributed training, inference of billion and trillion parameter models, like the sorts of ChatGPT, GPT-3, and even in the vision context and multimodal contexts. So we leverage different kinds of hardware and software advancements, optimizations to fine tune different frameworks, different algorithms, which help scale deep learning algorithms faster and better. So prior to this, I was a research scientist working in large language models, particularly for financial organizations like Morgan Stanley and HSBC. I am also one of the members of Google Research working on their Albert project, where I contribute. So, um, in this case, we'll be looking at one of the interesting applications of framework optimization. So, before we start with IPEX, we must understand that what do we mean by a deep learning framework? So, a deep learning framework is a framework or a compilation of different algorithms, different code snippets, which enable us to write better code in terms of training, in terms of inference, in terms of building different machine learning models. So when we leverage these kinds of things, optimizations from different kind of frameworks, we use different kind of kernels, right? So these kernels are basically any kind of compute kernels. So it may be gem multiplication, or it may be addition, or it may be any kind of bit manipulation. So fundamentally, these kernel optimizations is what makes these frameworks very much efficient in large scale training and inference. So coming to that aspect, two of the most popular frameworks that we see today in the market are Google TensorFlow and PyTorch from Meta or Facebook. So both of them have their own advantages and disadvantages, but the main similarity between these two frameworks is the way how they approach different models, right? How they compile different models in low-level code, machine-readable code, and process data and churn out the data. So let's say you are building a vision model to identify, for binary classification, for example, cats and dogs. The way you write the code in TensorFlow and PyTorch may be different, but underneath the hood, it is the same graph optimizations, graph level computations which is being done. Mathematically, we say that deep learning has different kind of calculus and different kind of computes, right? Involving finding the gradient, perform derivatives, Jacobians, and whatnot. But these, when we look inside a computer memory, how they are written, these are in the form of atomic kernels, which are dedicated to perform certain compute operations. Can be multiplication, can be exponentiation, can be not some nonlinear abstraction like that we see in the activation units, right? Softmax and sigmoid, right? So it can be many things. So with the help of these we know that ChatGPT is one of them. We know stable diffusions is one of them. And since the advent of the transformer models, right, BERT and all, these frameworks have been, of utmost importance to help deliver, enterprise applications and also to scale through large, clusters of GPUs, TPUs, and whatnot. Okay. So today we will be focusing on PyTorch, understanding what PyTorch is all about. It is a framework which was made by Meta. So PyTorch is a deep learning framework which has three different blocks, I would say, in the form of its architecture. If you can see the screen, we have a Python API through which we write the code. So using PyTorch, as it is mentioned in the PyTorch documentation or in the official site, the Python API is what is being used by people everywhere when they write when they write training applications or inference applications using the framework. There are different submodules inside this Python API. The standard one is the torch, which involves everything related to Pytorch in general. So this means setting up a variable, setting up containers. By containers, I mean vectors or tensors, which are used for computation, matrix multiplication, and other stuff. You have the second module, which is called as a torch autograd. This autograd has a very interesting capacity to perform derivatives. Now, derivatives are very important because in machine learning or deep learning 101, it implies that whenever you are trying to optimize a loss function, that optimization in the case of supervised or semi-supervised learning always implies a gradient minimization. That means you find the point where your loss curves actually converge, right? So the idea behind this is you want to reduce the amount of error that you predict and your machine predicts. In the case of deep learning models, this becomes a very high dimensional problem, right? Multiple dimensions are there. So this multifold dimension reduction is done by the autograd. This is an entirely mathematical library which employs different mathematical computation tools like advanced concepts of extrapolation, right? Expansion, series expansion, and other stuff to help perform these kinds of Jacobian derivatives efficiently. The third module you see is the Torch NN module, which is the building block for creating neural networks. So in Torch, the way we write any kind of neural networks, let's say a simple perceptron, which is known as a dense layer or a linear layer in the case of Pytorch, is wrapped in a neural network torch.nn submodule, right? So whatever we write in Pytorch using the Python API is invoked through the torch.nn module. The next part is multiprocessing. Now, this is a very powerful tool whenever we move out of one device and try to move to another devices. Let's say, in the case of large-scale, training, you are having a very powerful NVIDIA GPU or an Intel GPU, AMD GPU, right? And you want to offload your work of training from your CPU to your GPU, right? So that particular power of intercommunication between the CPU and the GPU is offloaded to this particular fellow, this torch multiprocessing. We will be focusing more on this aspect because IPEX relies heavily on this particular optimization path. And Pytorch uses this particular module known as the distributed module of Pytorch, which it helps in sending data to and fro across multiple GPU clusters. Because the fundamental difference between a CPU and a GPU is that in a CPU you have the capacity to order your instructions, but the GPU does not have that flexibility. That means you have to feed in the memory in chunks, right, to allocated positions, and you have to instruct the GPU. You have to inform the GPU, right, what instruction it has to perform. CPU has its own way of scheduling stuff. So CPU is like the master, and you consider the GPUs as your kind of workers, right? So this is the general terminology which is used in the case of Torch distributed when you are leveraging distributed training and inference across huge number of clusters. The Python API has this particular part. Now, if we go below, that is, if we are unwrapping Python API, the entirety of Torch is written in C or CPP code, C++ code. The three important modules inside the CPP code is autograd, A10, and JIT. Autograd is, just like I said, it is the C++ counterpart for efficient performance, right? For speeding up computation performances when you are doing Jacobians. A10 is another mathematical, I would say, library backend of Pytorch, which is used explicitly in neural networks. Where they are used in stuff like optimizing softmax activation. They are used for performing certain tricks inside your backpropagation, right? What kind of tricks? So it can be like, let's say, in a huge transformer model, like let's say BERT, you are having certain stuff like layer norms and different kind of tricky stuff inside there. So this A10 backend provides the support for two things. One is the compute, smaller computes of these fused activations, and the second thing it supports is the is when you are using that in a distributed environment, how you synchronize your results from across your GPU clusters, right? So A10 works coherently with another module which I have not mentioned called as the C10D for distributed when you are actually training and inferencing on large clusters. So A10 is a very powerful tool in this case. And the JIT is the third module is used for optimizing at a graph level. So let's say when you unwrap an entire Pytorch model which you have written in Python code, right, you are going to see the graph level instructions. There is a similar counterpart in TensorFlow, but since we are talking about Pytorch, the JIT is something which enables you to compile and make your graphs ready at runtime. If we are thinking in the terms of TensorFlow, it will be called as eager execution, right? JIT stands for just-in-time compilation. Now, whatever lies below this mid-level engine comes under the low-level library. Now, this is where this is typically known as level 0 in the case of your any kind of hardwares, right? So when you are interfacing these A10, JIT, and mid-level engines with your submodules, right, inside just below that low-level library, you are going to get a lot of hardware-specific instruction sets, customizations, custom compute kernels, which can be optimized further. So this is what the entire Pytorch ecosystem looks like in a nutshell. It is very huge, but this is what it is in a smaller way. So some important points which I want to mention, apart from what I have told, is that all of the internal workings of any deep learning framework leverages LLVM. Okay, LLVM is the fundamental soft kernel layer above your level 0 of your hardware, right? Which is used for which is used by different frameworks, right? Not only your PyTorch or TensorFlow, but any deep learning framework that you see online, right? JAX and all of them leverage LLVM for performance, right? So the most significant kernels are A10, Autograd, and JIT, right? And whenever you are using different backends, so let's say if you are writing code to offload your training to CUDA devices, right? Multiple CUDA devices, not only one graphics card, but multiple cards, right? In that case, what happens, you are going to use the distributed framework. There are different distributed frameworks for your different hardware devices. In the case of CUDA or NVIDIA, it is called as NCCL, NVIDIA Collective Communications Library. Or in the case of Intel, it is called as CCL, which is dependent upon the one API, right? One API collective communication library. Okay, so this is used for multiple, multi-sharded, training and inference stuff. Now, we are going to look into a little bit depth about what the CPU and the GPU architecture is and how it is important when we are writing some custom kernels, when we are, performing this kind of writing code for PyTorch, and where exactly the optimizations come in the case of IPEX, right? So as I have said, that whatever code we write ultimately goes to level 0. Okay, so there are two ways how we activate level 0. Is that one way is to ensure that we pass whatever components, that is including the data and the model, inside your GPU drivers. And inside the drivers, there are dedicated caches and dedicated execution units or compute units, right, where these are being performed. And it is always important to remember that this level 0 is very atomic. That means inside a GPU card, you are going to have a small section which only performs your addition operation. Similarly, you are going to have a small section or a small instruction set which performs your multiplication operation. Whatever optimizations at a hardware level that you can do, or at a level 0 software level that you can do, is to optimize that small part of memory or the instruction set so that it reduces bandwidth, it increases your throughput, it increases your runtime performance or your accuracy. If you're interested in, by accuracy I mean the amount of correctness of your data. Okay, so these are very atomic kernels which are independent for each GPU. So what happens, so let's say if I am the CPU, right, and I have a few friends who are the GPUs, right, and if I say to one of my friends to do an addition operation, so he may complete that faster. Now let's say if I tell my second friend to perform a huge matrix multiplication, he might be doing that a little bit slower because it is a very large compute. So in that case, what happens? And let's say I want to synchronize the results from the addition and from the multiplication. So what the CPU will do, or what I will do, is I will wait until my slowest process, in this case the huge matrix multiplication, gets completed, and only then I will move to the next step of the process. Right? So this kind of synchronization between the CPU and the GPU is where distributed frameworks thrive. Whatever we see, the large inferences, in chatbots, right, or in the case of any kind of inference, vision, multimodal, clip, DALI, whatever transformer architecture inference you see, all are in large cluster, all are based on this, right? So that is why there is always a requirement to have a huge amount of resources, compute resources, when you are building large models like GPT or something like that, even BERT and all. So yeah, moving to Torch distributed, because it is a very interesting thing about this, is that this is how it looks like as a distributed architecture. So if I go back just 2 slides back, so this is where I am looking into Torch multiprocessing, which includes the distributed framework, right? So so we write only the applications part, and sometimes these applications may not have the optimizations needed for us. So we can also go into this submodule layers. This DTP is what is known as distributed data parallel, which is Pytorch's way of ensuring parallelism across your GPU and your CPU if your CPU is multi-tied, right? So we will be looking into this a little bit depth. So what happens is, let's say you are writing an application for your CUDA device or your XPU device for Intel, right? So what happens? You are going to offload a part of your a part of your data to your XPU devices or your CUDA devices, right? Or GPU devices, or in the case of TPUs, like also in the TPU devices, right? So because your CPU has the data, in Pytorch, we use the data loader to load the data. Sometimes what happens is, if you want to load if your CPU has the data, but since you are trying to compute it on the GPU, you need to send the data to the GPU, right? It can be any accelerator devices. From now, I'm going to tell GPUs and XPUs as accelerators. So you are going to send the data to any accelerator devices. And why that is required? Because think in this way, is that if the CPU has the data all the time, and the compute is on the GPU, then the GPU has to request the CPU for each chunk of data all the time. And this is going to increase your latency of training, and this is going to give a very bad training and even worse performance in inference, right? So what you do is that you send your chunk of data, right, back to your accelerators. Directly you offload that to the accelerator so that the data is there and the accelerator can work on that. GPUs can work on that. So this particular strategy is known as data parallel. That means across your different devices, accelerator devices, you are sharing the data. You are creating a replica shard of that particular data, right? So that each GPU can work asynchronously, and they can update, like all of them, if they complete, they will wait until the slowest GPU completes, and then they will update the CPU. This is known as the data parallel structure. Okay, and in PyTorch, this is known as DDP, distributed data parallel. Okay, now distributed data parallel requires certain process groups. Okay, so process groups means that let's say PyTorch will actually create a kind of a group. A group is a kind of a collection of devices having certain ranks. Ranks are nothing but, let's say for the time being, they are IDs. Okay, so let's say GPU 0 is rank number 0, GPU 1 is rank number 1. Okay, any accelerated devices with IDs, and these IDs are all working together or maybe independently to perform certain operations, any compute operations, right? So Torch DDP, the task of Torch DDP is to ensure that this is done correctly, that in a group, like all of them perform the work independently, or if they are working on together, they perform it correctly and they return back to the external process, that is the CPU outside the Torch. Okay, so that is what is called as the process groups. Process groups means that Torch creates a collection of accelerated devices, a subset of them, where a certain computation units revolve. Okay. Now, what happens is a small piece of info on this. There is also a concept of master and non-master ranks or non-master accelerators inside a particular process groups. Master process group means that let's say Torch is like a teacher, right? He has created a section of students, and let's say 5 students, for example. And for in those 5 students, let's say student number one is doing the addition, student number two is doing some non-linear compressions, to student number three is doing some Jacobian derivatives and certain other things, right? So now for the teacher to know that whether all of them have completed their instructions or not, the teacher should not ask all of them, right? Should not need to ask all of them. So he or she can elect a representative on it within that particular student group, and that student group will ensure that everyone has completed their tasks. This is known as your master rank, master accelerator. Okay, so Torch process group is the teacher, and your master accelerator is like the representative of your student group. So that person is like holding the gates or holding the answer, that he will wait until all of them completes the evaluation, and then he will send it back to the process group. Okay, so this reducer that you see, this reducer is nothing but any kind of computation, mathematical computation, right? So this is how Torch distributed works in the case of data parallel. Now, before we go into data parallel, right, I want to into the CPU GPU architecture. I want to talk about something else. Yeah. So I talked about the data parallel. The second way is the model parallel. Now, as the name suggests, model parallel is nothing but you are splitting the model across different shards. This is very complicated. Now, you must be saying that, I have split the data, right? What is the drawback of data parallel? So the drawback of data parallel is if you are having limited number of memory RAM in your GPU devices, accelerated devices, and if you have large amount of data, your GPU memory is going to get crushed. GPUs have smaller memory than your CPUs in originality, right? So if you are offloading a lot of data to the GPUs, it might impact your performance, and it might not run, it might crash. So model parallel is another strategy which involves sharding some parts of the model. Very interesting. So sharding some parts of the model. Now, let's say you have a compute operation, right? Or rather a Torch NN module or a neural network architecture written in Torch, where you have kind of 6 layers, right? So what you do is that let's say you have 3 devices, okay? 3 accelerated devices, GPU 1, GPU 0, and over here it is 4. But let's say you have up till 0 to 2, okay? Now, what you can do is that you select any kind of layers between them, and you offload them to each GPU devices, right? So let's say, for example, you want to offload layer 1 and layer 3 to GPU 0, and layer 2 and layer 4 to GPU 1. Okay, so this particular abstraction of, or I would say offloading of different parts of the model to different GPUs is known as model parallel. And this is very tricky. Why? Because let's say your layer 3, for example, in this case, depends upon the output of layer 2. So in that case, it becomes a little complicated, because you want to ensure that your GPU 0 has completed its operations, right, before you send your results to GPU 2, which has layer 3. Okay, and due to this model parallel, right, model parallel kind of strategy, it becomes very important that when you are sending acknowledgements or data across your accelerated devices, there should be kind of good communication. No one should be waiting for a long time. There should not be any starvation in the network. There should not be any kind of hard and fast rules, like let's say waiting in the network, right? Otherwise your training will suffer. So this is what model parallel is, right? So we have different kind of collective algorithms, right? NCCL that we saw, the NCCL is now used over here to ensure that your your chunks of data from your different layers get offloaded quickly, and does not bottleneck any part of your network in your network who is doing the communications between the different layers or different GPUs, right? Efficiently, right? So this model parallel is a very interesting thing, and model parallel is the way how you can actually shard off parts of your model, and you can effectively perform compute operations way faster. Okay, across your GPUs. So, to summarize what we have learned so far regarding PyTorch, right? Before we move into the CPU stuff, uh, so PyTorch is a deep learning framework, and it has a very important application when we leverage large scale training and inference. Okay, and for that we have different kind of tools, and different kind of modules which we just saw performing different kind of operations, and ways to actually optimize those operations. This is the de facto baseline PyTorch, right? So let's talk about the CPU and the GPU architecture, right? Because this is where it gets interesting and how IPEX optimizes this. So let's say the left-hand side is your CPU and the right-hand side is your GPU. So your CPU has so many stuff, right? You see DRAM, you have L3 cache, L1, L2 cache, right? And your GPUs, you have DRAM, L2 cache, and these are all slots. These are all L1 cache and control. Control means control units. Okay, so these are all slots in a certain GPU. This is the CUDA architecture in like in a way non-technical way, but this implies that in a GPU, right? You in a GPU slot you have to effectively say which block. By a block I mean a contiguous memory location where a certain kernel, let's say that kernel does only addition, is going to be operated. Okay, so let's say for example from random ID, let's say 012, right, or 0ab, for example a random ID, to let's say 5ab, right, in the memory, this contiguous memory block you reserve only for the addition kernel, okay, in the GPU. And this kind of offloading, right, this kind of offloading and segregating or pointing the area or the location of the block inside your GPU memory is done with the help of either CUDNN CUDA framework, or in the case of Intel it is SYCL kernels, SYCL kernels, runtime kernels. Okay, so both of them are open sourced and both of them perform more or less the same operations. But allocation of this memory is what is interesting, because this, once you allocate the memory and you put the kernel there, the rest of the stuff goes into level 0. That means, which we'll be looking now. So this is the architecture of what level 0 looks like. So let's say this is where you are, right? You have your CUDA core, which has this is for the CUDA GPU, NVIDIA architecture, right? So you have your CUDA core where you offloaded your compute kernel, right? Addition kernel, and inside that core in level 0, you are going to have your different units or blocks. Those blocks are called, let's say in other words, they are called as execution units, for example. Okay, so what they do, they create certain threads, because CUDA is based on SIMT and SIMT, right? Simultaneous multi-threading. Okay, so CUDA is based on that. So they impose simultaneous multi-threading to spawn new threads and create new to allocate to different processes. Okay, so as soon as you write a compute kernel, let's say for example you write a simple code in PyTorch which does that, and you are going to see that. Let's say you write torch.nn.linear, certain layers, right? And you say some activation units. Okay, you are just passing that particular layer having a certain activation units. So what it will do, it will break it down into certain components. So based upon the activation unit, it will first dedicate a particular space area inside your GPU memory, right? It where the compute is getting performed. That will again get offloaded to the level 0 where threads are getting spawned, and then the different kind of computations are getting created. These are on the right hand side. So these threads are operating on this block of area. In CUDA terminology, this block of area is known as grids. All right, grids. Okay, so in many cases, what happens is, let's say you are doing softmax optimization, right? Softmax activation, right? You are going to need the data, X data, right? For that, it has to. So each of that grid level 0 will send a memory, a bus to the cache. Whether if the data is present in the cache, right? It will first search in the cache. Else, it will go to the DRAM inside your GPU, this particular block. Okay, if it is inside the cache, it is well and good. It will be very fast to perform that particular computation. Else, it is going in the DRAM, then it will be a little bit slower. So from a hardware's perspective, right, this is where your IPEX does the stuff. So the same level 0 architecture is there for the Intel, right? So if you miss in the L3 cache, right, so it will go to your DRAM. And this execution unit is something which is known as, in our Intel terminology, it is known as your level 0 stuff. Okay, so think about this, that if you were to optimize or write an instruction set which is able to send data to and fro your GPU, right, from your cache to your execution unit where the core computation is being performed in your grid faster, then it will definitely help. It will speed up the process, right? And think these are atomic kernels. That means, let's say a 1 millisecond difference, 1 millisecond is too high. So let's say 1 microsecond difference in your addition or your compute operation for that particular kernel, right, using that instruction set gets compounded when you just increase everything. Let's say you are doing trillions of computations, right? At the same power, raw power, right? You have 600 watt cards, you have 300 watt cards. At the same power capacity, the number of instructions you are processing increases because your hertz is increasing, your frequency is increasing. So what happens? Your instructions are getting compiled way faster, and that in turn that actually leads to a faster performance. Okay, so from a hardware perspective, optimizing the instruction set is what launched, created IPEX even faster. Okay, so this was a little bit overview I wanted to give before we go into IPEX. Okay, so so this is just the, I would say, an introductory session on the PyTorch part, right? So some of the resources are linked in this in the details, right? In the next part, okay, I will come to this collective calls later. What are these collective algorithms? But let's move to the Intel extension for PyTorch, what it is. Okay, now if you see this, right, this is what the broad overview of the architecture is looking like. So for example, this eager mode and graph mode is nothing but what we see in PyTorch, standard PyTorch. So, and if you remember, this is the Python API on which we write our code, right? Which we write our code just like using normal Python, right? The second part, A10 ops and graph ops, is where your middleware lies. If you compare it back to the image of PyTorch, general PyTorch, which we first saw, it is the same. This is the middleware where your CPP backends are getting linked, particularly performing on Intel CPUs and Intel GPUs. Okay, so mostly all of the distributed large clusters running worldwide, okay, for inferencing, for training, all of them leverage somewhere Intel XPUs, okay, as Intel CPUs. Okay, so let's say Amazon or Google or anywhere. So let's say ChatGPT, for example, that is also running sometimes inference, offloading inference to CPU, right? So writing instruction sets which optimize these kinds of A10 ops, that is the standard PyTorch middleware, to optimize performance, to run that particular code snippet or kernel faster, is where the benefit comes. This is even more pronounced when you're using Intel GPUs, right? So there are certain GPUs which are there out in the market exclusively, right? Which are working for extremely large, national labs, right? Like space labs across the world, right? Popular space labs which everyone knows. So they are using these XPUs and CPUs together to streamline the performance. Okay, but in our case, we are going to see the CPU performance, since since the GPUs are not exclusively out in the market, right? We can see that. One important thing is that the kernel's part is where most of the optimizations of our A10 or graph is done. So in the case of Intel, right, my colleagues and I, we work on the 1DNN framework. 1DNN framework is the neural network library framework of Intel, which is used for anywhere, right, training or inference, right. So that is the one framework which is used for any kind of creating deep learning libraries in the case of IPEX or any framework. And this one MKL, right, is the I would say math kernel library framework or the mathematical library framework, which is present in every deep learning library or framework that you see. You have Pytorch, you have TensorFlow, you have JAX everywhere. So everywhere you have MKL support, math kernel library. MKL support is something which Intel, because you are going to first run your compute on your CPU, right? So the math kernel library, right, is optimized for your CPU so that your operations does not bottleneck on your CPU, right? So for your GPU, it becomes XMX or GPU kernels, okay? And the level below this, so let's say from here, one API here to towards the end, this is where it is a part of your level 0 or SYCL runtime. SYCL means cyclomatic. Cyclomatic is the CPP equivalent of CUDA for Intel CPUs and Intel XPUs, Intel GPUs, accelerators. Okay. So in this case, we perform these kinds of optimizations, vectorizations, and different kind of custom kernels, right? Using the 1MKL framework, using the 1DLL framework, right, for our CPU and GPU to perform optimizations faster. Okay. So this is what IPEX does. It uses the standard Pytorch, uses the abstractions of standard Pytorch, and from the middleware, right, from where the A10 ops comes, from where the graph comes, right, from there it abstracts everything and performs optimizations at a lower level software, kernel level software, and even the hardware instruction sets. Okay. But for us, when we use it, it is just a one library installation which performs everything for us. Okay. So there are three different, I would say, two popular different aspects of this. IPEX offers extra performance boost on CPUs owing to dedicated AVX 512 VNNI. VNNI is a standard for Intel which performs operations faster on 512 instruction set. Okay, so these are certain dedicated instruction sets on your CPUs, right, which perform, just like I said, certain operations faster. Particularly, these are focused on two things. One of the thing is combination or fusion of certain mathematical operations. Let's say certain kernel additions, certain kernel divisions, or something like that. Okay, and the second important thing is it depending upon the hardware or your CPU tile architecture, right? It increases the bandwidth. It increases the bandwidth. That means your data to and fro transfer between your intra CPU tiles. So the CPU has generally a tiled architecture, right? So inside your CPU cores, so that is also done beautifully. Okay. So for there are the eager execution mode is also there, right? So one of the eager execution mode which I told was about the fusion operations, right? So IPEX optimizes PyTorch graphs through using the same methods as the standard PyTorch. So the standard methods such as JIT, they are getting used, right? We have the same abstraction that when we write the code. That means we are going to use the same code that we use in standard PyTorch, but internally the custom kernel which was written for PyTorch baseline is now changed to IPEX. Okay, internally. So it is important to say that PyTorch bindings are for CUDA specific, right? When you write PyTorch code, it has specific bindings to CPP bindings to CUDA, right? So this is Intel's way of optimizing performance when you are not only iterating over your CUDA devices but also your Intel XPU devices. Okay, and the second important thing is AMX. AMX is matrix multiplication, advanced matrix multiplication. Okay, so Intel has a new CPUs as of now, which is known as the Sapphire Rapids. Okay, and whenever we talk about deep learning, right? Whenever we want to talk about very large models, we always have to remember that large models are power hungry, right? They will take a lot of power for compute, but that power is also dependent upon the data type that you are processing. So let's say you are processing a float 64 data type. Obviously, it is going to take up a lot of chunk of memory as compared to B floats, let's say a float 16 or float 32. Bfloat 16 is another optimization which is known as brain floating 16, floating point 16. Okay, it's an optimized memory allocation for allocation data type, which speeds up certain computations. Okay, so generally what happens is, let's say the BF16 does not itself perform this addition or multiplication operations, because BF16 does not have that capability. So what we do and what these frameworks do is that to speed up the performance, they load the data type of the input to your model as BF16, but internally there is some interconversions to FP16 or FP32 as and when required by your software, your kernels, optimized kernels, right? And then they back process it back to BF16. So this is how the BF16 ecosystem works. The why we need this BF16 is because it is faster while data transfer during the data transfer stage. But during compute, BF16 is not that much stable. So because if you know about the instruction sets, right, IEEE instruction sets, in case of bfloat 16, you are going to get certain overflows, which is not recommended. The other important thing is about these kind of Intel CPUs, right, which is now running everywhere, is the tiled architecture and the feasibility of transferring data at a high bandwidth frequency, right, between the two tiles, and the context switching. As we all know, right, from general OS, that context switching is like the I would say the main bottleneck when it comes to processing, right, scheduling tasks. So context switches are handled efficiently, not the standard round robin scheduling that we see, but also a very efficient way. So this, in the case of IPEX, we can also use Torch DDP, that is the distributed learning framework that we saw. So IPEX, it provides a great support for that. It just leverages faster, right? When we have a kind of distributed data parallel, model parallel kind of structure. And the last thing I had already mentioned is that it combines a new instruction set for combining large matrices into a single operation, thereby speeding the computes. Okay, so this is the baseline of benchmarking for BERT. And as you can see, with different versions of data types, that is FP32, right, with the standard scalable Xeon processor, that is the Intel Xeon processor. And what is the latency, right? Inference time is the measure of latency. How fast is your process doing inference? Okay, so as you increase the number of cores, right? So let's say 32 cores, right? So your your inference time goes down. Of course, you're increasing the number of cores, but when you include this in the inference data sets, right? So you see the standard Pytorch with FP32 on a standard. This is the baseline Pytorch, by the way, on standard what we have learned before. This gives inferences like 1134 milliseconds. That means 1.1 seconds, right? But if we use IPEX optimizations, it goes down to let's say 254 milliseconds per inference. So it is that much fast. And imagine this is inference on a single batch. Now, if we increase the batches and if we are doing multiple batch kind of inferencing, how fast it will go? How fast it will go? Now, in the case of optimizing deep learning workloads, we have certain concepts called as quantization. Quantization is nothing but changing data types to increase performance, save bandwidth, and just transfer data to and fro devices or accelerators efficiently. All right. So in quantization, without even using quantization, Intel extension performs way better than the standard Pytorch. Okay. So this is already I have mentioned. So this is just for any kind of readings if you want to do. So this is the performance for a different wide range of models. Okay, this is the wide range performance of models. You have vision models, right? You have mostly different variations of vision models. Which bfloat 16 as the IPEX is getting used. Okay, so as a measure, you can see that almost for ResNet, right? ResNet 10. Let me go to ResNet 50. ResNet 50 is the, it's like the, I would say, the first neural network library which is being used everywhere, right? Since its inception, right? So a very important model in the vision world. So using this, you are getting almost 2.11x better when you are using, let's say, IPEX with bfloat 16 over FP32. Okay, and these results are all reproducible in the notebook which I have attached, and also the links which I have shared, right, which I will be showing in a little bit. Um, and these are certain ending notes which are highly technical, right? So I have talked about the Intel CPUs. Now, whenever we have, if you have access to Intel XPUs, right, GPUs, in that case, the optimizations are even better because Intel GPUs, discrete graphics cards, are using certain things called as matrix extensions, which we are working on. So it is like a kind of an optimizer which does the standard optimizations what is there in IPEX, but also certain device specific optimizations. So for example, right, let's say you are doing the forward pass on your GPU card, right? So instead of saving certain flops, so instead of running certain flops, you save certain flops of instructions by let's say bypassing them. Okay, by bypassing the by bypassing means that you are actually pre-allocating certain memory locations, pre-allocating certain compute operations, and comparing them, right, before actually doing the computation. So this is known as a bypass mechanism, which we use for XMX for internally speeding up the processes, right? This is very efficient when we have this kind of quantizations, when you have this kind of bfloat 16, int 8, FP32, FP16, this kind of interchange of your data types for training and inference. All right. And also, devices which have larger caches will always benefit you. The recent set of CPUs which Intel has launched, the Sapphire Rapids, is highly efficient in the case of cache, bandwidth and all. And I think most of the labs are using, even cloud labs, online labs. Everyone is reverting to that. Okay, and and just in a nutshell, I want to say that how do we use that, right? For us, for the normal people, for example, how do we use that? So this is how you do. I mean, import Intel extension for Pytorch as IPEX. You have to transfer your model to something called as a channels last format. Channels last means it saves your CPU bandwidth by compressing certain channels through which the input is coming. Okay, and this IPEX.optimize is your, I would say, your bread and butter. I mean, IPEX.optimize is like entire. It performs all the optimizations that you need to do. All the optimizations that you need to do. So let's say quantization, memory reduction, bandwidth compression, let's say device transfer, optimal device transfer, offloading, everything it will do. Okay. So depending upon your hardware and your CPU, particularly for CPUs as well as for XPUs, it will do that for you. So yeah, and this is certain major optimization technology, methodologies that we employ. This is actually a very technical thing, but I wanted to highlight this, is that there are three ways how we can optimize, okay, for the frameworks. One way is to use the operators. One way is to optimize the graphs. Graphs means the graphs for Pytorch has a backend graph, right? So in this case also we create a backend graph, so optimize the graphs, and we optimize the runtime. So for the Pythons, for the operation specific optimizations, these include certain kernels that you are optimizing. So low precision bfloat 16 or int 8, ease of use of bfloat 16, auto mixed precision like Torch AMP. We have the support for IPEX as well. Auto mixed precision is nothing but transferring data to and fro in different data types. Data layout optimization in your tiled CPUs, cache locality, which we have already talked about. The second part of optimization comes from the graph. Right. So graph, how you are optimizing the graph, fusing the graph nodes. Let's say you are doing batch normalization. You are fusing that with one conv layer, right? Convolution layer, convolution node, actually. So you fuse that. This is known as kind of folding, how you are folding the network, convolution folding, right? So these kinds of fusion of different fusion operations, they rely on the format NCHW or CNHW, depending upon if you have an image vision model on an image data set. So channels last becomes very efficient in that case. So op fusion for better cache locality. This is very important because if you have a good cache locality where you can readily refer your next operation, it becomes very good. You speed up a small atomic process by 1 microsecond, you get a huge runtime efficiency. At the end, like for a larger model, and in runtime, thread execution, stream execution, right? Memory buffer pooling, GPU runtime, and launcher, right? So these for the runtime aspects, how you are segregating and launching your kernels in a proper way, how you are performing streams in a proper way, right? How are you performing pooling, like combining together pooling in a correct way? Okay, so these are the three standard of operations where we try to optimize better. And yeah, these are the standard links for those. I mean, um, for whatever GitHub link, blogs, if you want to read, there are lots of blogs available on IPEX where you can try it out. There is an entire model zoo with all kinds of models, all of them, right? Whatever you see in Hugging Face, if you are familiar with Hugging Face, it is almost there in the case of the model zoo. Okay, we have optimizations for there as well. So I think for the demo, right? So we'll be mainly seeing how the way to write the code, because the results are self-explanatory and you can run those notebooks, from the repo itself. So if I come out of this and so I just created just let me reload this once, right? So if you can see the screen, right? So this is a notebook which I created, right? Which I and my colleague created, right? So this is also a part of standard Pytorch, which is there, which is present in the link which I mentioned, right? In the Pytorch talks also, you will find IPEX linked there. So this notebook, I and my author and my colleague from IPEX, right? We created this. So this shows the way how you can actually write code using Intel extension for Pytorch. Okay. So for example, let me go to the interesting stuff where you can see where you can actually try it out. So let me talk about the inference part, because that is a little bit easier to understand. So inference is tricky because inference, you do not only need to have a kind of I would say, a forward pass. You do not need to have a kind of a backward pass in that case, right? Backward pass means back propagation is not needed. So if you do inference on BERT, right, the benchmark which I showed, and right, in that case, you just need a small two-line code changes to optimize your BERT model. It is that simple, right? So apart from these two lines, import IPEX and model.optimize, effectively all the things are just the same that you write in a standard, Hugging Face BERT inference code, right? If you are just looking for the performance, that is hyper speed inference, right? So you just need to add these two lines and it will automatically optimize your model for you. Okay, it will perform any kind of pruning, any kind of reductions, any kind of compressions, quantizations, whatever it has to do, it will do it. And you are going to get this a lot more performance, very high, I would say, throughput on your particular CPUs. Okay, so this is the straightforward example how you can do that, right? So I added most of these examples, and I did not link the output because I think that this is also has a collaboratory link. You can run them yourself. I mean, if you run them, you're going to see, you can set a timer and you can exactly plot what is the result of this. So this is just a preliminary repo. I will be adding more samples to this particular repo. That is why I created a repo. Otherwise I would have handed a notebook. So the point of this repo is I will be adding more distributed samples, because this is the Python way which we allow our users, or which we recommend our users to use. But let's say if you want to write at a more fine-grained level, that would include you to write at C++ level. Okay. So in the slides which I shared, there is a link to advanced Pytorch, right, for DP and MP, where I use CPP code. It is one of my repositories, right, where it is a you accelerate your Pytorch framework using CPP backend. That means you work with the middleware of Pytorch, not on the outer layer. Okay, so I will be adding those in the IPEX in due course of time, but it is also there in the links which I shared. Right, you can also refer from it. But we recommend people to use the optimized Python kernel because it is good, faster in this case. So you have CIFAR FP32 training in the case of your in the case of your IPEX. So here too, apart from this particular line and IPEX.optimize, right, you do not have to perform anything. So you do not have to add any line of code actually. So what it will do is it will automatically take up the model, and you need, if you want to specify an optimizer in the full training phase, let's say Adam or fused ADA, this kind of optimizers, then IPEX will able to optimize that particular optimizer better as well. Okay. Now this is for single CPU, single GPU training, which is okay. But what happens in the case of distributed data parallel? Now this is where it gets interesting. Now the ResNet distributed data parallel, the way to write a code is to first, I would say, initiate a kind of a process group for PyTorch, right? So this is done by this particular line. Dist is nothing but torch.distributed, right? So the way how torch distributed works, as I mentioned analogically, right, using the teacher and the student example, is that you create a process group, and this process group is how will you create a process group? By specifying the ranks, which are ranks to the IDs to the particular accelerators, and you specify a communication mechanism, how you are going to communicate between them, right? Generally, the communication mode is through the TCP method or the standard environment method, where you specify the port and the address, how you are going to intercommunicate between the different accelerator frameworks, accelerators, or the GPUs or the GPU tiles, right? And this is how you write, initiate a process group for torch distributed. And while infusing Intel extension for PyTorch, right, since you are trying to run it on your distributed cluster, right? So IPEX, whenever you are trying to run it on a distributed cluster, let's say GPUs, right, you are going to rely on Intel XPUs. Intel XPUs. Intel XPUs have the one API, like all of Intel framework has the one API. One API, like as I mentioned, like it is the one DNN, one MKL math kernel library. So one MPI is also important for this one CCL bindings for PyTorch. Now, what is this? This is actually another framework from us Intel, from the framework team, right? Which actually is used for the collective communications library. Now, if you recollect, I told about NCCL, NVIDIA Collective Communications Library. This is collective communication library for Intel, one API. Okay. So in the case of NVIDIA, you have to write, import NCCL or something like that. Okay. So it in a way it performs, different kind of algorithms are there again for collective communications. Just let me highlight that, just in case if I miss out, I forgot to highlight that. So collective calls are nothing. There is a section on this, right? So let me see. Yeah. So collective calls are nothing but how you transfer the data to and fro. These are certain algorithms, right? They include broadcast, reduce, reduce scatter, all reduce, all to all, and all gather. There are again different other algorithms, but these are the main ones. So what they do, this is a depiction of what they do. Broadcast means that from the master representative of your student group, you are sending the data to each of the fellow students. Okay, so this is known as broadcasting. Gathering means from all of them you are collecting the data. Okay, now this is very tricky. All reduce, the reduce I could not reduce, and all reduce are actually used for the computation. How are you going to compute? Let's say your student 2 depends upon student 1's output, right? He has to take the student 1's output and he has to multiply with his result, and he has to send to student 3. So there is a dependence on each of the GPUs on each other. So what happens, most of the frameworks, they communicate this data transfer across your GPUs or your accelerators in the form of all reduce mechanism. Okay, all reduce are different kind of all reduces are there. Hierarchical all reduce, cyclic all reduce, right? There are different algorithms for all reduces, right? Tree algorithms, right? You have Raman-Seifner's algorithm. So these algorithms are nothing but how you are going to allocate or send the data without causing any bottleneck in the network while you are transferring the data. Okay, so all the compute part, this is known as the data transfer part. These two are involved in data transfer, even all to all. But reduce, all reduce, and reduce scatter, these are all involved in computations. Okay, these are all involved in certain computations, like any kernels computations or something like that. Okay, so just in a nutshell, I wanted to talk about that because it is important since we are talking about the NCCL and 1CCL libraries. Okay. And the rest of the part is again the same line of code which gets repeated. We initialize a distributed data parallel, which we talked about in Pytorch by using this particular line, distributed data parallel. What it will do, it will shard off your data across your different GPU accelerators or XPU accelerators. And this is the way how we write, in the case of DDP for IPEX. All right. So these are some of the important points which I wanted to mention. And in the links, I have this particular blogs. This contain all the set and this links, and this link actually contains all the samples, all the resources that you want to take action, right? So I will be adding more resources in due course of time on the CPP backends and all on the same repository, right? So yeah, and that's all in a nutshell. I hope you learned something from this. You can try IPEX, you can try Intel extensions, and let us know how it works. We'll be more happy to have your feedback on this. But across Intel's devices, this will greatly boost up your performance and all. Okay, and these are my social links to GitHub, LinkedIn, and Twitter. Right, you can. I'm active mostly on GitHub, right, LinkedIn. So you can, if you face any issues or if you are looking to, work on IPEX. Use IPEX for very large scale model, distributed model inference training. Just let me know. So that's all that I wanted to mention. And lastly, I want to thank global AI community, for organizing this. It's very beautiful. And I really enjoyed. I'm glad to be a part of the session. So thank you to the global AI community. That's all from my side.